In Chapter 6, we turn our attention to the normal distribution. The normal distribution is a continuous distribution like the ones that we talked about in Chapter 5, which were the uniform and the exponential distributions. However, the normal distribution is far more important than the uniform or the exponential. It is the most important distribution that we deal with for a number of reasons, but it's also, unfortunately, quite often misapplied and misused. Not everything fits a normal distribution. A lot of things do. If you were to, I think the book has an example of if you were to sample the shoe sizes of, thousands of people, and then you created a histogram from their shoe sizes, you would see that it fits a bell curve very nicely. It's very symmetric. A lot of data is that way. It fits a bell curve, and a normal distribution suits it well. However, not everything fits a normal distribution, so we just need to be careful not to over-apply it, but nevertheless, it is very important, and it does show up in a lot of places. The notation for the normal distribution is here. X is distributed as n, the normal distribution, with mu and sigma as the two parameters. Mu, remember, is the mean, the population mean, and sigma is the population standard deviation. Some quick review about density curves. We talked about these in Chapter 5. Remember that when we started out, we were dealing with discrete distributions, and so we had reasonably sized lists of values that were possible outcomes for the data, right? So because they were reasonably sized, we could make a table that would include everything, and that was our probability distribution. But with continuous data, there's too many possibilities because it's continuous, right? It could be any value between, say, 0 and 1, and there's an infinite number of possibilities between 0 and 1. So we can't list out all those possibilities anymore, so we switch to graphs. And so remember that the density curve is the graph of a continuous probability distribution, and that there are a couple of important things to remember. Number one, the total area under the curve is equal to 1, and that's important because the area under the curve is equivalent to the probability of a certain event. Every point on the curve must have a height that is greater than or equal to 0, but less than 1, right? Or less than or equal to 1. So we can't have any negative probabilities, so therefore we can't have any negative values on the curve. All right, so in section 6.1, we're going to start by discussing the standard normal distribution. The standard normal distribution has a specific mean and standard deviation. Okay, the mean for the standard normal is 0, and the standard deviation is 1. Okay, so all the time, always, for the standard normal, the mean is 0 and the standard deviation is 1. So if, on the other hand, just to kind of preview what we're going to do in section 2, if we don't have a mean of 0 and a standard deviation of 1, we can actually convert any normal distribution into a standard normal using a z-score. Okay, and we find the z-score this way. This is the formula for it. X minus mu divided by sigma. Okay, X is just a particular data value. Okay, X is just one data item. So every single data item in a population has its own z-score. So X minus the mean divided by sigma will tell you the z-score for that particular data value. Z-scores are interpreted in terms of the number of standard deviations that the value is either above or below the mean. So if we were to calculate the z-score and we get a z-score of 2, that tells us that that data value is 2 standard deviations above the mean. Okay, on the other hand, say we got a z-score of -3. Okay, that would tell us that that particular data value is 3 standard deviations below the mean this time. Okay, if it's negative, that means you're less than the mean. If the z-score is positive, that means you're above the mean. If you happen to get a z-score that is 0, then that means that that x value, that data value, equals the mean. All right, this is the shape for a standard normal curve. I am leaving out the function itself that defines this curve. It's listed in the textbook if you want to look it up, but it's a kind of a big ugly thing, and there's absolutely no need to memorize it, so I'm not even listing it here. If you're curious and you want to look it up, you're welcome to. But notice that the peak of the curve is at 0, where the mean is, and the curve tapers off on each side, so that by the time you get to 3, okay, at that point we are 3 standard deviations either above or below the mean. The graph is very, very close to 0. Okay, now this is an asymptote as it gets to the x-axis, so it never truly gets to 0, but it gets very, very close to 0, to the point where eventually we get so many decimals that we call it 0, but it's technically not. All right, so just to kind of give you a quick example, brief example here. Suppose we have a random variable x that is distributed as a normal distribution, okay, with a mean of 5 and a standard deviation of 6. All right, that tells us that we have a normally distributed random variable, mean of 5, standard deviation of 6. So let's find a couple of z-scores and see if we can just kind of interpret what this means. So suppose that x is 17. Okay, x is a particular data value. We want to find the z-score, and then we want to interpret what it means. So we plug this into our z-score formula. Plug the 17 in for x, 5 goes into mu, 6 goes into sigma, and it gives us a z-score of 2. So that tells us that 17 is 2 standard deviations above the mean. All right, now suppose we do x equals 1. We want to find the z-score and interpret this. So 1 minus 5 over 6 gives us a z-score of negative 2/3. So this tells us that 1 is 2/3 of a standard deviation below the mean. So we'll talk more later about the z-scores and then using them for calculations and whatnot. But at this point, it's just kind of important to understand how you find a z-score and that interpretation regarding the number of standard deviations above or below the mean. So why are z-scores nice? Z-scores are nice because it allows us to compare data that are scaled differently. Meaning, say you have data that refers to the same basic idea but are in different units. So like say you did a survey of heights in the United States and you measured that in inches, and then somebody else did a survey of heights in, say, Germany, and you use centimeters. Okay, well, those two units might not be real easy to compare, but if you took a single person's z-score in the United States and a single person's z-score in Germany, you could compare how they stack up relative to the populations. Okay, so a z-score of 2 means that you are quite a bit taller than the mean. A z-score of negative 2 means that you're quite a bit shorter than the mean. So even if the data have different units, we can use z-scores to compare them. All right, so let's look at how we're going to calculate some probabilities involving the standard normal using the calculator. And actually, I'm going to try to give you this in a little bit of broader terms than just the standard normal. I'm going to show you how we can also change the mean and standard deviation if necessary. So our procedure, or our function in the calculator, is normal CDF. You probably have seen it. You may not have paid any attention to it, but if you hit second vars and go to the distributions menu, normal CDF is number 2. And if you hit enter on it, if you have the newer style calculator where it gives you a prompt, it prompts you for 2 things. The lower, well, 4 things, but the first 2 are the lower and the upper. Okay, so the lower bound is the lower of the 2 z-scores, and the upper bound is the higher of the 2 z-scores, assuming you have 2. So if you have 2 z-scores and you want to find the probability that something happens between those 2, then you enter in the lower and the upper. And at this point, we're going to leave mu as 0, and we're going to leave sigma as 1. But in the future, we may want to use the calculator to save us the trouble of having to find a z-score. If you convert to a z-score, you never have to change mu and sigma. It can stay 0 and 1 forever. But if you would rather let the calculator do the work of calculating the z-score, then you can just put in the lower x value, higher x value, and then the mean and the standard deviation, and it'll do all the work. So I usually don't give my regular stats classes of choice, but with STEM stats here in the summer, I'll give you the choice. I think you guys can make good decisions there. On the other hand, say instead of trying to find the area between two z-scores, or the probability between two z-scores, say we just want to find the probability of a less than. Okay, so we want to find the area to the left of a particular z-score. In that case, what we would like to tell the calculator is to go from negative infinity up to the upper bound. Problem is, we don't have a negative infinity button on our calculator, so instead what we use is scientific notation. We do -1 times 10 to the 99th. And the way you do scientific notation in your calculator is you hit the second key and then you hit the comma button, which is just above the 7 key. And you'll notice above the comma button there's a little EE. There's 2 E's there. That is the note. That's just, for whatever reason, that's the way your calculator describes scientific notation, is that EE. And I've never bothered to look up why it's EE. Maybe somebody will do that and share with us. I don't know. But anyway, we're telling the calculator -1 times 10 to the 99th because in terms of the calculator, that's close enough to negative infinity to give us a good answer. All right. So area to the left. Remember, the lower bound is -1 e to the 99th, and then in the upper slot you put the actual z-score for the upper bound. Now, suppose you want to find the area to the right. We do the same thing. I see a typo. We do the same thing except we do the lower bound, and then we do +1 e to the 99th. I will fix that in the slide, so if you are looking at the slides after you view this video, that negative will not be there. It should be lower bound and then +1 e to the 99th. Because similarly to over here, what we want to tell the calculator is go from our lower bound to positive infinity, but we still don't have an infinity button. So 1 times 10 to the 99th gives us a big number that's close enough to infinity to give us a good answer. So that's how you find probability using normal CDF in your calculator. So we're going to look at an example here. I'll show you how we go through this. This is thermometers that are supposed to give you a reading of 0 at the freezing point of water, 0 Celsius. So let's assume that they're distributed according to the standard normal. So the mean is 0 and the standard deviation is 1. We want to find the probability of a thermometer find the probability of selecting a thermometer that reads less than 1.58 degrees Celsius at the freezing point of water. So basically what we're describing here is there's going to be a little bit of manufacturing tolerance in these thermometers. They're not all going to be perfect and read exactly 0 where they should. So we want to know what's the probability that we randomly pick one that reads less than 1.58 degrees Celsius at the freezing point of water, which it should, right? If it was made correctly, it should read less than that. So let's see. The way we would go about this is we go second bars, normal CDF, and in the lower slot, because this is a less than question, we're going to put -1 e to the 99th, and in the upper slot we're going to put 1.58. This is basically giving us the area under the bell curve from negative infinity to 1.58, which is equivalent to saying everything less than 1.58. The mean is still 0, the standard deviation is still 1, so if you hit paste on that, it should pop this that I have in blue up on your screen, and then you press enter and you should get 0.9429 for a probability. For example, part 2, put 1.2. What is the probability that we pick a thermometer that reads between -0.5 and +1.5? So again, we go back to normal CDF, only this time we have 2 values to put in. We're not going to use that 1 e to the 99th thing. For the lower we put -0.5. For the upper we put 1.5. We leave the mean and the standard deviation alone, 0 and 1. And then when you paste that and hit enter, you should get 0.6247. So this time what we have done is we found a probability between 2 z-scores. Alright, now let's for a moment check out what would happen if we didn't have our calculators. Alright, z-score tables, the normal distribution is so common and so useful that they have when I say they, people, mathematicians, statisticians, have created tables full of z-scores and their associated probabilities. So if, I don't know, if you don't have a calculator, or your calculator's not working, or you don't like using the calculator and you'd rather do it this way, this is a second option. I've really not run into any students that would rather use the tables, but I want to show you because they're so common that you may have a professor that requires you to use them, no calculator or something, who knows. So looking at the table that I have attached in Classroom, we're going to find the probability for selecting randomly selecting a normally distributed value with a z-score of 1.54. So we want to know what's the probability we get less than 1.54. So let's switch over to that table. Okay, so here on the second page we have positive z-scores in this first column, and I want to go down to the row for 1.5. Alright, remember we're trying to find the probability of selecting something less than 1.54. So here's the 1.5 row, and this is the 0.04 column. Okay, notice 0.04 here at the top. So if you put those together, 1.5 and 0.04, you get 1.54. So this value here is the probability of getting something less than 1.54, because notice here at the top of the table it says table values represent area to the left of the z-score. So everything to the left of 1.54 is equivalent to saying the probability of less than 1.54. Okay, so 0.93822 is the probability that we're looking for part A. Question number 2 asks, what's the probability of selecting something greater than negative 0.24? So if now we go back to the first page of the table where we have negative z-scores, we want negative 0.24. So we're going to go down to negative 0.2, and then we have to, let's see if I can get the top row in this screen. There we go. So negative 0.24. Okay, right here, 0.40517 is our probability for less than. Okay, remember, we were asked about greater than, but our table can only give us less thans. So we have to do a little bit of math. 1 minus 0.40517 gives us a value of 0.59483. Okay, 0.59483. That's the probability of getting greater than negative 0.24. For the third question, we want to know what's the probability of getting between negative 0.8 and positive 0.65. So what we're going to do here is we're going to find both scores in the table. Okay, first we find negative 0.8. Well, this is negative 0.80, right? So the first column in this table is the 0.00 column. So we want negative 0.80. That's 0.21186. Okay, we just kind of keep that, write that down, keep that handy. The next one we want to find is positive 0.65. So positive 0.65 would be on the next page. We go the 0.6 row, and we go over to the 0.05 column, and we have 0.74215. So 0.74215. Now, if I want to find the probability of getting something between these two, between 0.65 and negative 0.8, then what I need to do is I need to subtract their areas. So I'm going to do 0.74215 minus, the other one was 0.21186, and when we subtract those we get 0.53029. Okay, that's our probability for the third one. That's how we do the betweens on the table. So it's up to you. If if the z-score table makes sense and it's easy to follow, then you might want to use it some in the homework. If you really don't like it and would rather just use normal CDF, then go for it. Alright, so now we need to talk about going the other direction. Okay, so instead of finding the probability of a specific x value, maybe we want more of a percentile type of thing, where we want to know what's the number that would give us 95% on the bottom and 5% on the top. This would be equivalent to asking what's the 95th percentile. Well, with the normal distribution, there's a couple ways we could do it. Okay, with the calculator, there's a function called INV norm, inverse normal. And that's number 3 in that same menu that we've been using to find normal CDF. Okay, so second vars, number 3 is inverse normal. Now, on most calculators, it doesn't prompt you for anything but area. It says area, mu, sigma. Okay, the area we're looking for would be the area to the left. So we would type in 0.95 for the area. And then we go down to paste, and we get 1.64485. We'd probably round that to 1.645. Okay, 1.645 separates the bottom 95% from the top 5%. But perhaps we don't have the calculator again. Okay, the second way to do it would be to look at the table. And basically what we're looking for is in the body of the table here where we see all these probability values, we want to try to find the one that's as close to 0.95 as we can. So it looks like between these two values here, the probability jumps from 0.94950 to 0.95053. So right in between those two values is where the correct answer lies. So that would be 1.6 between 1.64 and 1.65, okay, which agrees with what the calculator told us. So 1.645 fits right in between these two values. So if you have the calculator, that's probably the easiest way to get the exact decimal. If you don't have the calculator, then the table works just fine. Now this homework looks like a lot more than I typically give you, and it is. It's about 20 problems, but like I said before, the standard normal is pretty important. There's a lot of things in here that I want you to get very comfortable with doing, both normal CDF and inverse normal and finding z-scores and all of it. So you know, as always, this is just for your benefit. I'm not going to check and see that you did it, but certainly this would be a good homework to spend some time on. And let me know if you have any questions. Thanks.